I hope my screen is also visible now. In our previous sessions, we have counters and we have also started with this counter development in our previous sessions, and we have seen how to achieve your frequency division by 5, frequency division by 3, and how to achieve this mod 3 counter, and frequency division by 2, frequency division by 4, frequency division by 8 we have seen, and this and all things we have seen in our previous sessions. I hope these are all you have watched the recordings. Sorry, this recording is not yet uploaded. That will be uploaded soon. Okay. Yes. Now, in this particular session, we are going to start with frequency division by 3. In our previous sessions, also we have discussed about frequency division by 3, but it was 33.33 percentage and 66.66 percentage. That frequency divisions we have seen in our previous sessions. Now, in this particular session, we will discuss about frequency division by 3 and frequency division by 6 with 50 percentage duty cycle. Let us try to understand this and wait a minute. So in this particular session, we will discuss about frequency division by 3, frequency division by 5 and frequency division by 7 with 50 percentage duty cycle. Let us try to understand how to achieve 50 percentage duty cycle. In our previous sessions also we have discussed this frequency divisions, but where we have discussed with 33.33 percentage duty cycle and 66.66 percentage duty cycle. But in this particular session, let us try to understand how to achieve this frequency division by 3, frequency division by 5 and frequency division by 7 with 50 percentage duty cycle. Now, let us say I want to achieve frequency division by 3 with 50 percentage duty cycle. So this will be my, I will take one reference clock. This will be my reference clock I am going to take. So this is my clock. And if I want frequency division by 3 with 50 percentage duty cycle, then my on time period should be 1.5 and off time period should be 1.5. This is my requirement. So the on time period, let us take it as 1.5, and my off time period, this is 1 and zero point 0.5, and my off time period will be 1.5. Okay, so I'm going to take 1.5 and 1.5. Okay, and again it will turn on here. So total your clock cycle, this is first clock cycle, second clock cycle and third clock cycle. If your clock is completing 3 cycles, then your output is completing only 1 cycle and you are getting 50 percentage duty cycle f by 3. That is nothing but t on is equal to 1.5 and t off is equal to 1.5. If you consider this, then you are going to get 50 percentage duty cycle. Now, I want to get this type of waveform. I will draw it one more time. So this is my clock. These are my positive edges of clock which I am going to consider. So my output should be 1 for 1.5 cycles and it should be 0 for next 1.5 cycles. And again it is 1 for next 1.5 cycles and 0 for next 1.5 cycles. So this is the requirement which I am having. Okay, this I should achieve using my Verilog code. Now how to achieve this? So for achieving this, I am going to take two enable signals, enable 1 and enable 2. I am going to consider two enable signals, that is enable 1 and enable 2. Now this enable 1 signal is going to become high. This will become 1 when, and let me take one counter also. For frequency division by 3, previously I have took mod 3 counter. Here also I am going to take a mod 3 counter. So this mod 3 counter is going to count like this. This is count 0. Next is my count 1, 0, 1, 2. So this is my mod 3 counter which I am going to consider. And I am also going to take two enable signals, enable 1 signal and enable 2 signal. If my enable 1 is equal to 1, my enable 1 should become 1 whenever my count is equal to 0. When count is equal to 0. Only in this condition, my enable 1 will be equal to 1, else enable 1 will be equal to 0 itself. Okay. And when should your enable 2 should become 1? That we will see. Okay. So here my enable 1 will become 1. Let me draw it with another color. It will be clear. So this is my enable 1 signal, which is becoming 1 and which is becoming 0, and again it is becoming 1 here and becoming 0 and so on. Okay, so this is my enable 1 signal and this is my output. This is the output which I should get. Okay, now coming to enable 2 signal, when should this enable 2 signal become 1? Now if you can see, I should have this extra cycle also. This extra half cycle I should have. So that's why for achieving this extra half cycle, what I am going to do is I am going to make this enable 2 signal to 1 whenever my count is equal to 0 at negative edge of clock. At negative edge of clock. And this count is equal to 0, your enable 1 is becoming 1 at positive edge of clock. At positive edge of the clock. Okay, so this is the difference which I am going to consider. My enable 2 signal will become 1 if and if my count is equal to 0 and if there is a negative edge of the clock, and if my enable 1 will become 1 if and if there is a positive edge of the clock and count is equal to 0. Okay, so here the positive edge of the clock we have got enable 1 is becoming 1 and it is becoming 0 at next positive edge of the clock. Okay, now how your enable 2 signal is going to look like, let me erase this. So your enable 2 signal is going to become high whenever your count is equal to 0. Your count is equal to 0 at this edge and you have a negative edge. So up to here your enable 2 will become 0 and here your enable 2 will become 1 and in the next negative edge it will become 0. Here it will become 0. Okay, and again when it will become 1 and again it will become 1 here and it will become 0 at this edge. At this negative edge it will become 0 and so on. Okay, so this is my enable 2 signal. This is my enable 2 signal. Now if you simply can see one minute, give me a minute. If I want to get my output, if I want to get my output, then what can I do is I can simply make OR operation of my enable 1 and enable 2. Please perform the OR operation between enable 1 and enable 2. You will get your output like this. So your enable 1 is becoming 1 here and it is 0, enable 2 is equal to 0. OR operation of 1 and 0 is nothing but 1. It is becoming 1 and at this edge your enable 1 is becoming 0 but your enable 2 is 1 only, right? That's why your output is still 1 only. And at this negative edge both are becoming 0, so this is also becoming 0. Okay, like this we will get our output. So simply what are we going to do is we are going to perform OR operation between your enable 1 signal and enable 2 signal for getting your output. That's it. So this is how we are going to develop a frequency division by 3 circuit with 50% duty cycle. Let me write down the steps for this. So you need to develop a counter, that is mod 3 counter you need to develop. And next step is you need to consider two signals. One is enable 1 and another is enable 2. Enable 1 should be high when count is equal to 0 and this counter is basically a positive edge counter. Okay, and enable 2 signal should be high when count is equal to 0 only, but it is happening at the negative edge of the clock. It is happening at the negative edge of the clock. And simply our output is nothing but OR operation of enable 1 and enable 2. We will get our output. So these are the steps which we are going to follow for getting frequency division by 3 with 50% duty cycle. F by 3 with 50% duty cycle. Yes. So is there any doubt or any queries? Have you understood what are we going to do for achieving frequency division by 3 with 50% duty cycle? Any doubts or any queries? Let us try to implement the same in our tool. Now let me create a file. Next, create file f by. So the file has been created. Now what are the inputs and outputs? We already know. Simple inputs are input clock reset, and we have enable signal. So this enable signal is basically used to make your circuit work. If enable is equal to 1, then only your circuit is going to work, or else your circuit should not work, that is you should not get any output. Okay, and we have output rich frequency division by 3 with 50 duty cycle. This is our output that we should have. Okay, now internally we will declare one counter, mod 3 counter. So mod 3 counter we will have it of 2-bit counter. Okay, and we will declare two enable signals, enable 1 and enable 2. Okay, two enable signals have declared. Now within an always at the rate passage of clock begin, if I apply my reset signal, my counter should be equal to 0, enable 1 signal should be equal to 0, and enable 2 signal should be equal to 0. And since it is a sequential circuit, I am going to use non-blocking assignments. Okay, and followed by else if enable is equal to 1. If enable is equal to 1 and my count value is equal to 2. Okay, my count value is equal to 2, then what should I do? I should make my counter to 0. My counter should become 0. Else if my enable is equal to 1 and count is less than 2, then my count will increment. Count is equal to counter plus 1 tick binary 1 followed by end. This is counter. Okay, I have declared it as counter. Okay, and followed by end. So this is the code which I have written for my mod 3 counter. Okay, let me write down the test bench also, or let me copy it from this particular thing. Simulation source, go to simulation source, frequency division by 3, or you can also copy the mod 3 counter test bench. Let me open this file and let me create one more file, f by 3 with 50 percentage duty cycle underscore test bench. Press ok and press finish. Not this one. Okay, let me search it. F by 3 by 3 with 50 percentage duty cycle test bench. Open this file. Yeah, and I will paste the mod 3 counter code, and here I'm going to change the design name. My design name is f by 3 with 50 percentage duty cycle is my design name. Let me paste it over here. Is my test bench underscore tb is my design name, clock reset enable, and my output is frequency division by 3. Okay, and here I will declare my output as frequency division by 3. Okay, and reset I've applied enable. Okay, that's it. Let me make it as a top model. First of all, let me save these two files. Just I've copied the code which I've written for my mod 3 counter, the test bench. I've copied it, and first what I'm going to do is I'm going to check whether the counter is basically achieving or not. Let me set a stop. So let me add the clock signal and counter signal to my waveform window, and let me relaunch it. And let me add the clock signal also, add to wave window and relaunch it. So my counter 0 1 2 0 1 2 0 1 2 0 1. Let me zoom in a little bit. So it is just simply counting. It is a mod 2 counter we have achieved successfully. Okay, so there is no mistake in that. Now let us write down our main design code. Let me open that. So this is my design. Now here what I should write is I should write down the enable logics, enable 1 and enable 2 logic. So for that I am going to take one more always block. So always at passage of clock begin. Now what should I do? If my count is equal to, so what we have seen in our design, our enable 1 should become 1 if my count is equal to 0. Okay, so if my count is equal to 0, then my what should happen? Then my enable 1 should become 1. Okay, one tick binary 1. Okay, and followed by else my enable 1 should become 0. My enable 1 should become 0. This is the requirement I have, and followed by end. Okay, now within another always block, what I'm going to write down, always at the rate neg edge of clock. Neg edge of clock, this is counter, not count. Neg edge of clock, what should happen? Begin if my counter is equal to, what is the value we have taken? Counter is equal to 0 itself. Counter is equal to 0. My enable 2 should become 1. But at neg edge of clock, counter is equal to 0. My enable 2 should become 1. Else, my enable 2 will be equal to 0, and followed by end. Okay, so this is the code which I have written, and let me save this. And what should we write down? Assign our output. What is our output? Let me declare it as by f by 350 duty cycle. This is my output. Let me copy this. That should be equal to enable 1 or with enable 2. This is the thing which I have written. Okay, let me save this and run this. And what do you think, whether it is going to work? So anyone who already know Verilog, can you answer whether it is going to work or not? And let me add those signals to the waveform. Go to scope and DUT, press on objects, and you can add this enable 1, enable 2, counter, and f by 3 underscore DUT at the wave window. Okay, and let me relaunch it. Now let us check it out. Whether it is going to work or not, let us check it out. So this is my counter. This is my counter which I am getting. And let me go to the initial point. Yeah, this is my clock. And where is my output? This is my output. So if you can see your output, it is high for 1 cycle, 2 cycle, and another half cycle also. So your output basically it is a high for 1, 2 and half cycles, and here it is high for 1 and half cycle, and again it is high for 1.5 cycle, but initially it is high for 2.5 cycle. Why it is so? Let us see. Your enable signal, if you can see, it is becoming 1 here, and when it is becoming 0 again, it is becoming 0 again here, it is becoming 0, and it is becoming 1 again here at the positive edge of the clock, and yeah, and again if you can see, it is becoming 1. So initially because of your counter value, it is 0 from initial state, you are getting this extra cycle. You can neglect this particular cycle, the very first pulse you can neglect, and from the next pulse you can check it out. So your frequency division by 3 with 50% duty cycle, your output, if you can see here, it is high for 1 and half cycle, and it is low for 1 and half cycle. Okay, and again 1 and half cycle it is high, and 1 and half cycle it is low. Okay, so this is nothing but your design, where you are designing it using your enable signals logic. Is it clear? Any doubts or any queries in this? So, how to remember this type of circuits is just draw the waveform. Okay, just draw this output waveform. So we already know how to design a frequency division by 3 with 50% duty cycle. The waveform we already know. So just follow this logic. How to get this? You can consider your enable signal such that you should get your output waveform like this. Is it clear? Any doubts or any queries in this? And let me explain this waveform again. So this enable 1 signal is becoming 1 whenever your count is equal to 0 and clock at the positive edge of the clock. And again, your enable 1 signal is becoming 1 here whenever your count. Yeah, this thing I wanted to explain. Okay. Let me explain you what is happening. So initially, if you can see at the first positive of clock, your reset is applied. So that's why counter was equal to 0. And your enable signal, let me add all the signals inside my waveform. DUT, I will add reset and enable signal. These two signals inside my waveform. So I can show you something. So this is my counter which I have. If I apply my reset signal, then my count is equal to 0. And where is my enable was made to 1? My enable is made to 1 here. So that's why at next edge of clock, my enable was made to 1. So at this pause edge of clock, my counting process has started. Okay, 0, 1, 2. Okay, leave these 3 cycles for now. And now see here, this counter value is equal to 0 and it is a positive edge of the clock. This counter value is equal to 0 and it is a positive edge of the clock. What are we expecting? What we have written inside our code, if enable and counter is equal to 0. If enable, if counter is equal to 0, my enable 1 should become 1. My counter is equal to 0 and it is a positive edge of the clock. My enable 1 should become 1 at this particular instance, but it is not becoming 1. Can you able to see here? Where it is becoming 1, whenever your count is equal to 1, it is becoming 1 here. Can you able to see this? Let me explain you one more time. Whenever your counter is equal to 0 and at the positive edge of the clock, your enable 1 signal should be 1, right? This is the code you have written. If your counter is equal to 0, enable 1 is equal to 1. But is it becoming 1? No, it is not becoming 1. Whenever your counter is equal to 1, then your enable 1 is becoming 1. And coming to enable 2, what you have written for enable 2, whenever at negate of clock, if your counter is equal to 0, enable 2 is equal to, counter is equal to 0, enable 2 is equal to 1. So at negate of clock, counter is equal to 0, enable 2 is equal to 1. Enable 2 is listening to our words, but enable 1 is not listening or it is not following our code. So you can see in the further also. So whenever your count is equal to 0 and if there is a positive edge of the clock, your enable 1 signal is not becoming 1. And whenever your count is equal to 1, your enable 1 is becoming 1. Can you able to see this and able to understand what is happening? Yeah. Now, what may be the reason? Did we written anything wrong, or is there any issue in the tool, or what may be the reason? Anyone wants to answer this? Did we written something wrong, or is there an issue in the tool, or is there an issue in our logic, or what is the issue? I will write down in the PPT also. What we have expected, let me change the color. What we have expected is whenever our count is equal to 0 at passage of clock, my enable 1 should become 1. But what is our result which we are getting? When count is equal to 1 at the passage of clock, our enable 1 is becoming 1. That is, after one cycle, our enable 1 is becoming 1. Now, what may be the issue? Okay, let me answer this. So this is a very important conclusion which we can get from here. Now, before answering this question, let me do a small change. Let me do a small change. What I'm going to do is I'm going to use blocking assignment. I'm going to use blocking assignment over here. And for count incremental logic also, I'm going to use blocking assignment. Okay. And for this enable 1 and enable 1, for this also I'm going to use blocking assignments. Okay. Let me save this and run this, relaunch it again. Let us see what is going to happen. And let me zoom in a little bit. Let us see what is going to happen. So you can see here, whenever your count is equal to 0, enable 1 is becoming 1. You can see at the same positive edge of the clock, your enable 1 is becoming 1. And whenever again your count is equal to 0, your enable 1 is becoming 1. But if we were using non-blocking assignment, your count is equal to 0, but it is not becoming 1. At the next cycle, your enable 1 is becoming 1. It is not following our code. Now, what do you think? Should we use blocking assignment or should we use non-blocking assignment? What will be our conclusion? Or is there any mistake in our logic? Let me answer this. So this is a very important conclusion. The first thing which we have already discussed is we are not supposed to use blocking assignments in our sequential circuits. So we should always use non-blocking assignments in our sequential circuits. That is for sure. Sir, but we are getting some mismatch in the functionality. But if we are using blocking assignments, then our functionality is correct, you might argue. Okay. Let me give the reason for that one also. First of all, I am not supposed to use a blocking assignment inside my sequential circuits. So let me turn it all my assignments to non-blocking assignments. Okay. Now, 1 minute. Yeah. Now let us try to understand the reason. What is it happening internally? So what we have written, we have basically written one always agreed passage of clock. We have written our counter logic. If reset my count is equal to 0, non-blocking assignment. Else my count is equal to count plus 1. Count plus 1 tick binary 1. Now, if we have written like this, then it is a mod 3 counter. Mod 3 counter. It is a mod 3 counter. And when you are synthesizing this, it is going to look like this. You are going to have 3 flip-flops. This is first D flip-flop. This is second D flip-flop. And this is third D flip-flop. Like this, you are going to have 3 D flip-flops. And this is Q3, Q2 and Q1. This is the counter logic. If you are writing it in Verilog, somewhat like this only your design is going to look like. Okay. So if you are writing a mod 3 counter code, it is going to look like somewhat like this. Okay. Not exactly. We will have some extra combinational logic. So to avoid the state 1 1. Okay. So you should only count up to 0, 1 and 2, right? So we'll have one AND gate which is going to control this not to enter into the state 3. Okay. That logic I'm not drawing here for simplicity. Now we will have one counter logic. Now what is another logic we have written? What is the another logic we have written? Simply always iterate pause edge of clock if my count is equal to 0, my enable 1 should become 1, else my enable 1 should become 0. Now what I am doing here, basically I am comparing. This is my comparing logic. Now how my synthesizer will yield a comparator logic like this. Okay, my synthesizer will yield a comparator logic like this because I'm writing a comparison. Okay, and whatever the outputs which you are going to get from this flip-flop, this count will be given to your comparator. This count which you are getting, which will be given to your comparator. Okay, and this comparator output is given to another D flip-flop, is given to another D flip-flop. Why it is given to another D flip-flop? Because you have written this comparison logic inside your always agreed passage of clock. So one flip-flop will be synthesized, and at the passage of clock you are going to get your enable one signal. Enable one signal you are going to get like this. Okay. I will explain it one more time. You are simply writing your counter logic. So one sequential circuit will be yielded, and the output of this flip-flop, output of this sequential circuit is my counter. This counter will be given to a comparator, and this comparator is a combinational logic, and this combinational logic output will be given to a sequential logic, that is a simple D flip-flop. Because you have written this comparison logic inside your positive clock, so you are going to get your output at the positive edges of the clock. Like this you are going to get your output. Is it clear? Yes or no? Please let me know in the chat box. Is the circuit clear? Now what is happening? Let us try to understand. This is my clock, and this is my counter, and this is my output of comparator, and this is my output of first D flip-flop. So no clock is given. We have applied reset signal. What is the value of counter? It is equal to 0 0 0. And what is the output of your comparator? Comparator is also equal to comparator. Your output will be equal to 1 because your count is equal to 0, right? And you are going to have output of first D flip-flop as 1. Okay. Next. So we will go on, and at the first clock edge, your counter value will become 1 0 0 1. Now this counter value at the first passage of clock, you are going to have 0 0 1. Okay, so this value will be updated to 0. Okay, but previously we have 1 which is present here before we are going to apply this first passage of clock. That's why at the first passage of clock also we are going to get 1 only. We are going to get 1 only, and your output of comparator will be 0 only, but your output of this flip-flop will become 1 because at the first passage of clock these two flip-flops are running parallelly. These two flip-flops are running parallelly. Your counter value is getting updated to 001. Okay, I will draw the clock also. This is my clock pulse. At this clock pulse, my counter value is updated to 001, and at the same instance, my output of this flip-flop is also given, and the value which is present before applying this first passage of clock is 1. So that's why here also I am going to get 1 itself. Okay, but your output of your comparator will be 0. At this positive edge of the clock, your output of the comparator will be 0 itself. Okay, now at the second clock edge of clock, at the second edge of your clock, what is going to happen? Your count value will be equal to 010, and what is the value which is present before applying this passage of clock to this D flip-flop? That is nothing but 0. This previous value, it is going to give it to the output. So your enable 1 will become 0. Okay, and what is your comparator output? It is 0. Okay, now at the third edge of the clock, at the third edge of the clock, your count value is equal to 001, 010, 011 we are not going to get, we are going to get 000. Okay, if we get 000 at the third edge of the clock, immediately what is going to happen? If we get 000, immediately comparator, because it is a combinational circuit, immediately it is going to give 1. Okay, but previously the input of your D flip-flop is having 0, and at the present edge of the clock your comparator value is 1 only, but the previous value before applying this third edge of the clock, your D flip-flop is going to have the value 0 which is present. That's why whenever you are applying the third edge of the clock, immediately the flip-flop output will be 0 itself, but your comparator value is 1. This 1 will be updated to the output of this D flip-flop in the next cycle, that is in the fourth cycle. This present output of this comparator will be updated to the output of this D flip-flop in the next cycle. That is the reason you are getting this particular logic at your output. So is it clear? This is the logic. This is how somewhat it is going to look like. Okay, now so at the this positive edge of the clock, what is the output of this counter? It is nothing but 0 0 0. Okay, at this positive edge of the clock, your value is equal to 0 0 0. Let's say initially your comparator output is equal to let's say it is 1, sorry 0. Okay, so before applying this positive edge of the clock, the same clock is applied to these two flip-flops. Okay, before we apply this positive edge of the clock, before this edge arrives, the input which is given to this D flip-flop is equal to 0. That's why at this first positive edge of the clock, your output, that is enable 1, will become 1. Okay, here enable 1 is equal to, sorry, enable 1 will become 0 only. Okay, now at the second edge of the clock, what is your counter value? It is equal to 0 0 1. Okay, okay, let me erase it. Sorry, I have made a mistake here. So initially your counter value will be equal to 0 0 0. Comparator is, it is going to compare and it is going to give 1. Okay, so at the first passage of clock, your counter is basically coming to the state which is known as 0 0 0. Okay, and your comparator value is becoming 1 exactly at this positive edge of the clock. Okay, but what is the value which is present before this positive edge of the clock? That is, it is equal to 0. Before this positive edge of the clock, the value which is present to this D flip-flop was equal to 0. So that's why at the this first positive edge of the clock, our enable 1 is equal to 0. Okay, now at the second positive edge of the clock, what is going to happen? Your counter is going to count 0 0 1. So this 1 will be propagated over here. The previous value of 1 will be present before this edge arrives. Okay, and this value will be 0 at the second positive edge of the clock because your counter is equal to 0 0 1. So it is updated to 0 at the second edge of the clock. Your comparator output is updated, but the flip-flop output will be equal to 1 since it is having 1 which is already present. Okay, so it is going to sample the previous value of 1. Previous value. That's why at the second edge of the clock, enable 1 will become 1 whenever your counter is equal to 0, 0, 1. Okay, and whenever your counter is equal to 0, 1, 0, what is going to happen? Still your comparator output will be equal to 0 only. And what is the previous value which is present to this present at the output of your comparator? 0. That will be present at the input of your flip-flop before your third edge of the clock is present. So exactly whenever your third edge occurs, your enable 1 value will be 0 itself. Enable 1 value will be 0. It will be updated to 0. This is what it is happening. Now is it clear? So once try to draw this diagram and try to understand the behavior, what is happening. Okay. So please remember this two logics are sequential logics which are running with the same clock. Okay. So since they are running with the same clock, they are not dependent upon each other. They are running parallelly. This is a parallel logic. Okay. Whatever the output which is present before this flip-flop, that particular value is sampled. Basically, it is sampling the previous values. Okay, but this is a combinational logic. It is basically sampling the present values. Okay, please remember this and try to once draw this circuit and draw the behavior and try to analyze it. Anyways, we are going to discuss it one more time in tomorrow's session also, because we need to understand the enable to signal behavior also. Okay, yeah, so that's about this particular session. Once try to analyze by on yourself also, and I will explain it one more time in tomorrow's session, and I will explain the enable to signal behavior also in tomorrow's session.